I'm going to talk today about challenges in developing a universal metagenomic diagnostic. I was kind of inspired by the musician last night who gave an extremely long, introduction explanation about the music that they were about to play, which was actually longer than the actual piece. So I was actually thinking of just telling you now most of what's going to be in my talk and then giving a short talk, but so I want to actually, so in that spirit, I want to just focus on one thing, which we're trying to do, and I think this is actually now, it's obviously, you don't know when you start doing something what you're trying to do, but sometimes in retrospect you kind of realize what you're building towards. So what we've been trying to do over the last, I think, 4 years is to build what we call the universal metagenomic diagnostic, which is an inexpensive, scalable diagnostic test that can detect any respiratory pathogen or in principle other kind of pathogen. And that's what we've been trying to do. And I kind of tell you where we are. And so what I mean by inexpensive, scalable, I mean something like you can do 5,000 or more tests per day, and it costs $20 a test. So something like that, if it existed, would be really transformative, because then we wouldn't be doing a flu test or a COVID test or something like that. We would just be doing this test, and then you'd know whatever you have. And if you really think about how far genomic sequencing has gone and things like that, it's kind of a failure of our society that we don't have this yet, considering that we could we can measure Neanderthal DNA, right? But if your kid is sick, you can't know what virus your kid has, right? So it's kind of doesn't, if you think of it that way, it doesn't make sense. Okay, so anyways, but it's not easy, and so there's many challenges, logistics, IT, RNA-seq, kind of the assay, bioinformatics database, and also regulatory. And we kind of made progress on all of these, and I'm going to talk a little bit about this. And so, okay, I'm going to kind of phrase it to these challenges and kind of what we get from. So I'm going to first talk about logistics and IT. So if we start with, this is what we want to get. So I'm going to talk about the first step for what we did, because I think the first step we did is we try to basically solve this problem, right? Which is a subset of this problem, right? Which is inexpensive, scalable diagnostic test that can identify one pathogen, right? So that's a start. And this is actually, some of you have heard about this work. So this is really something that we started during the pandemic, and the reason, none of those involved were involved in diagnostics or anything at all, but we were, this was if you remember back in 2020, this was the kind of news that was coming out at the time, in March 2020, what went wrong, it puts us at risk, Tom Hanks, you guys remember this? Tom Hanks, right? He's my COVID memory, he's one of my COVID memories. And then the NBA scandal, right? 58 tests, that was a big deal back then. And California was bought a $1.4 billion facility just to do testing, right? So we're thinking, and of course they sent us all home, and we really kind of had nothing else to do, because if you worked on a COVID project, you could actually go into the labs, and if not, you had to just stay home. And so it kind of created incentives. We were like, well, why don't we develop, we have all the equipment, we have sequencers, why don't we just develop a test? And so that's really how SwabSeq started. And we were thinking, okay, so if we were going to develop a diagnostic test today, we would use sequencers, right? It doesn't make sense to use PCR machines. And so that's how SwabSeq started, and it kind of came together really quickly. And so the idea behind SwabSeq is that it's a diagnostic test using sequencing, and the basic idea, there's two real ideas there. So the first thing is that we barcode all the samples. We add molecular barcodes at the very beginning, and then we mix all the samples together, and then we sequence them, and then we deconvolve them using computational approach, and then we can get individual level diagnostics for every individual that was mixed together on the sequencing. So so that's the basic idea. So what do I mean by barcoding? So molecular barcoding is obviously one of the kind of foundational techniques in genomics, right? But the basic idea is that, in this case, we're trying to amplify a part of the spike protein, and in the actual PCR primers, they add a little bit of additional DNA, and it's a different piece of DNA for every individual. And so this is a toy example. So for example, individual 1 gets 5 A's added, individual 2 gets 4 A's and a C, et cetera, right? And so then later, when we sequence the data, we also sequence the barcodes, so we get the barcodes, and then we can figure out, which reads which DNA came from which individual. So we find the individuals that have the COVID sequences, and we can say that those are the positives, and the ones that don't have it are the negatives. Obviously, these are not. This is a toy example, but it's the basic idea. And at kind of scale, you can imagine barcoding thousands of samples and then putting them all together. And in one instrument, you can do thousands of sequences together. That's really where, when we started, we didn't really know how things would play out. But in the end, that actually became really important because in our approach, we were able to do like 6,000 samples at a time on one machine, which is, like the typical machines do like 300 samples. So that made a huge difference. So how does the barcoding work? So in our case, we have the 2 PCR primers that are targeting the spike protein, and the barcode is actually hard-coded in those primers, and it's added to the sequence. And so essentially what in the lab, there's many different primer pairs, each one with a different barcode, and we have to keep track of which individual gets which barcode. We'll talk a little bit about that. So that's really one idea, is this idea of molecular barcoding. The other idea behind the technology is the concept of a spike-in, which is that it's the kind of thing that you can do if you're approaching this problem from a sequencing perspective that you couldn't really do if you're approaching it from traditional technology. So the idea is that we add a known quantity of DNA to every sample, and that specific DNA that we add looks very much like the target sequence that we're trying to amplify, but it's got 6 positions reversed. So it's close enough to the target that the PCR primers will always amplify it, but it's far, but based from the sequence, you can easily differentiate the two. So the idea is that your kind of readout, your measurement is going to be the ratio of like the kind of real SARS-CoV-2 reads versus the spike-in, and that it's kind of like normalizes, internal normalization. So here's actually kind of how it works. So this is a plot showing synthetic examples. So these are samples which were negative, and we added a certain amount of SARS-CoV-2 to each one. And so zero, the 0 is really negative samples, and then the positives are kind of different degrees of positive. So the farther they go there, the more was added. And then the y-axis is the number of reads that we see of the spike of the COVID, right? So you can see that, things kind of work here, right? So like the negatives, most of them are 0, right? And as you add more virus, you see that the amount of virus increases, kind of like the reads increase, right? But you can also see that it's not that accurate, right? Because if you're going to basically make a decision between what's positive and negative, you have to draw a horizontal line here. And so you can see that you're going to have a lot of problems because there's no real great place to draw that horizontal line, right? So that's a problem. But on the other hand, if you look at the ratio of the spike-in to the real, it's much more robust. And you can see that if you draw a horizontal line, it'll be pretty accurate. And I want to point out 2 specific ones. You see these 2, like this, something here is weird, right? So what that is actually, but then here it kind of pops up, right? So actually what's going on here, and this is a pretty common phenomenon, is that there's something in the sample that inhibits PCR. So the PCR reaction just doesn't work. But that inhibition will affect both the PCR on the actual COVID and also on the spike. So the ratio actually still preserves, so shows that it is positive, okay? So that's basically, so results in an accurate test. We kind of, based on this, we made this, this is like one of the weird thing about diagnostic testing is you have to kind of make a you can't really look at everything. You have to make a very kind of concrete algorithm, and then you stick with it, and then you evaluate it, and then that's kind of how it goes. So we came up with this, and it worked pretty well. We did some evaluations, and we actually, at this point, we went to our leadership. This was like in May, and we said, oh, we've heard in the news that there's some really testing problems, and we developed a technology that can solve COVID testing, right? And of course, these meetings are on Zoom, so I'm sure that they were hearing this and just cracking up, right? They're like, this is ridiculous, right? So, but they said, and this is what they said to us. They're like, look, we believe you that the genomic technology works, so we believe you because that's what you guys do. But all of the other components, the regulatory, the CLIA lab, the logistics, that's really hard, and we don't really see you guys being able to do it. We know how to do it because we're a health system. That's what we do. But there's a pandemic, so we're really busy. So we can't really help you. But if you want to try, like we have this couple little bit of space in this building that we're planning on making an institute in. If you want to be there for a few months, and please move your COVID testing outside of the human genetics building. If you want to just go there and try, sure, but we again, don't ask us for any help, figure everything out on your own. So we said, great, okay. So that's how the lab started, and we ended up, getting this great lab. We're still, actually 4 years later, we're still there, right? Because, things change. And we started building this lab, and we started with this whole, basically, we went from, developing technology in May, getting our FDA application in, operational pilot, all this stuff in July, and then finally we got our regulatory approval in October, and we started testing in November for UC Santa Barbara. So why UC Santa Barbara? Well, because actually the technology was really working already in July. We started testing the same people that the campus was testing. So some people were coming back to campus and they were being tested. We would test them also and show that our results were concordant in July. But we couldn't actually do any testing until we got our regulatory approval, and that was like both a CLIA license and the FDA approval until October. So we basically were just not really doing much of anything. And the university every week would call us and ask us, we'd meet with them, the leadership, and they said, do you have your license yet? No. Do you know what's coming? No, because you have no idea. It could have been years from the FDA, right? And so what happened was that the university really needed to do testing, so they ended up signing a contract with a different vendor. And then a week later, we got our license. So then we had this huge lab with like nothing to do. And so then they helped us basically start selling tests on the open market to try to make up the $5 million hole that we created. So that's kind of how it happened. So anyways, that's really what turned out. And so in the end, we actually were able to scale up to our lab. First, when we started, I want to say we were able to do about 100 tests a day, and then by the end, kind of now, we could do 25,000 tests a day, right? So I want to kind of talk about how did that happen? So in order to really, and this is it was kind of interesting, but we learned and it kind of makes sense now, is that there's really 5 different parts of the test. There's kind of the collection, there's the pre-PCR, which is, we'll talk a little about in a second. There's the PCR part, and then the post-PCR, which is kind of creating a sequencing library, and then the sequencing. And so, whenever you have as you're scaling from, let's say when we started with 100 up to, let's say, 25,000, you have to, different bottlenecks emerge at different times, right? So, at first, the real bottleneck was actually all of the logistics, like just collecting the test, getting them to the lab, processing all the stuff. And so that was the first thing that we worked on, which is that we had very few staff, and we kind of came up with our own processes on how to do this. And one of the things that we came up with was this idea that we would like at the collection sites, they would prepare everything for us. So they would put the samples. They put the samples into these racks, and then they would get when they came to the lab. And typically, what people do in labs is they open every sample. They take the swab out, and they take some of the liquid from the sample, and they transfer it into a plate, and it's called accessioning. And actually, that's both kind of a dangerous component because a lot of people can get infected from it, but also it's very labor intensive. We didn't have any of that kind of staff, so we came up with a different process, which is that the samples come into racks, and we would basically dump them into 95-degree water for 30 minutes, and then we would just put them on our automation, and that's how the test works. So in order to do that, we really needed to have all of our samples go into these very small tubes that would fit into these racks. And so there was no real collection things for that. So one of our, actually Valerie Arboleda, who's actually going to maybe at CGSI last week, she kind of had this genius insight that perfume funnels fit perfectly into our tubes, and she could buy them on Amazon. So she bought, I think we bought some on Amazon, they worked great, and we ended up buying 20,000 perfume funnels on Amazon, which was our starting collection kit. And then eventually we got them manufactured. We actually made 1 million, and we thought that would be all we would ever need, but we actually ended up buying a second million after we got that far. So anyways, that's kind of the thing. And so that's kind of that's the collectioning part. And so then that was one bottleneck. And so there's another bottleneck that we had to deal with was just, kind of keeping track of the primers and how that worked. And so the other idea was that, since every individual needs to have a different primer, and of course, let's say we're getting, let's say thousands of tests per day, it's pretty complicated to keep track of which individual got which primer. But that's obviously the way that you know who's, like you can connect the sequencing results, right, to the individual test. And so the way that we did this is that we kind of came up with this concept that we would kind of organize it kind of as follows. So the idea is that we would think of conceptually like we're processing 1536 samples at a time. And the way that would work is that we would have four plates of 384 wells, and each position in those plates had we had a known, we knew what the molecular barcode was, and in each of those plates you could put 4 sets of 96 samples. So we would basically be thinking of like 16 racks of 96 samples, and they would be going to these 4 plates. And so this kind of would be the layout. So you can imagine that you have 4 plates, and then you have these 16 racks, and there's basically 16 different positions on the racks. And so, for example, this is rack 2, which is in the second quadrant of plate A. So this is kind of, kind of the layout. And so every rack, when it would come in, or just before it would be processed, the tubes, there's these special racks that have holes in the bottom of the rack, and the tubes themselves have a 2D barcode on the bottom, and there's this machine that basically is a digital camera, and so you just put the rack onto this machine, and it would scan it, and it would generate a file that basically looks like this, which is kind of in every position what the barcodes are. And meanwhile, we also knew for every plate what the molecular barcode was. And so based on this, where, which rack went into which quadrant of which plate, our software would basically connect these two and say, okay, then this, and take the file up from the scanner and, and the file with the barcode and just the information of which rack went to which place, and then would connect that, okay, this patient sample gets connected to this, get this barcode. Then when we get the results from the sequencer, we basically split all the reads based on barcodes. We then run this algorithm. We get the diagnostic whether it's positive or negative, and then we would then decide, oh, this person's positive, based on that. This barcode's positive, and then based on that connection, with the software, we would say, oh, that barcode corresponds to this patient sample, so then this patient sample is positive, right? So that's kind of how that's how it would work. And then this actually approach was able to, we were thinking of these 1536, each one of those, so we had 1536 barcodes, each one of those could be put together onto, at a time. And so our lab was capable of doing 3 of those sets a day. So that was about 4,500 tests, okay? And so then, we're doing this, we're getting this work. This is actually in the summer, we're setting up the lab, coming up with this process, and then we're saying, okay, we kind of believe this is going to work. We go to the, we decide to buy supplies, and we decide that we're going to really do this, and so we go to the vendors, and we really need these specific tubes that have these barcodes at the bottom because the whole thing rests on that. So we go to the vendors, Thermo Fisher, and we say, hey, do you have tubes? They're like, oh yeah, we have tubes. Can we buy some? They're like, of course. You got UCLA is great partner, right? We obviously buy a lot of stuff from them anyway. They're okay. So how about we buy like 20,000 because we got the 20,000 funnels from Amazon. Thinking let's get 20,000 tubes to go with it. They say, oh no, we can't sell you 20,000 because obviously there's a real rush on supply. So we're only doing big orders. So we can sell you 800,000. But we can't sell you 20,000 tests, right? So we said, okay, well, how much is that going to be? They're like, okay. So then we go to our leadership and we say, look, here's the issue. We can't get any tubes. We can only get 800,000 tubes. How much is that going to cost? And they said, it's going to be $1.25 million. And they said, let's think about it. And then surprisingly, they said, sure. They're like, okay, because they thought that we would be testing, right? They didn't realize that little snafu. So next thing you know, all these supplies come in. And of course, we're not testing for UCLA, but we're testing for other universities and everything's going fine. And then if you guys remember, early 2021, right? Like around May, June, vaccines out, right? It really seemed like everything was done, right? So we thought that we were done and, we could basically go back to our other jobs. But of course, like Delta happened, right? And then the university decided that they wanted to test everybody they want to reopen the university and test everybody in the university when they came back to school. So that was going to be something like, like 10,000 a day, something like that. And so then we had because we were only able to do 4,500, so we had 2 bottlenecks. One is collection, again, that became a bottleneck, and then also how to process that. So for collection, at our peak, we had to collect 1 test every 3 seconds. So you can imagine that, like at that point, it's not practical to have some kind of staffed, system. So we were going to go to vending machines. So that's actually there's actually still some there. And so, but there's just, just to give you a taste of like what was happening, there are like limitless number of problems. So for example, the vending machines, great idea. They put all the tests in the vending machines, and then this would happen, right? So the tests were getting stuck in the vending machines, and people were trying to tilt them towards themselves, and it was dangerous because like these things could kill somebody, right? And so this required an innovative solution. It wasn't ours. It was actually the campus came up with. They realized that they put weights in the tests, they would drop. But weights are expensive. But candy per weight is inexpensive. So they put candy in the vending machines. But they're also it was not our idea. It was the campus. They're still kind of cheap. So they put only candies in the tests that went in the vending machines, but the ones that were distributed had no candy, right? And so there was like limitless discussions on Reddit on why there were candies in some and not in others. And of course, like are we adding, are we encouraging people to use candy before their test? Like, we didn't want to like touch that, right? So we just did not reply to or clarify at all, right? So that solved the collection. But then also the other problem with the 4500, so we actually, and of course, like, so so the way that we would make our primers, because primers were so hard to get, the quality control that we needed for this was much like more stringent than we needed for research. Because if you're doing research and you get a plate of primers and maybe 1% of them fail or 5, even that's not a big deal because you'll just redo them, right? That's not an issue. But here, if 1% fail, like that the test fails, right? So we couldn't really tolerate that. So in order to do this, we actually ordered all the primers set in large volumes separate. We would test them and then we would mix them on our like the forward and reverse on ourselves, with the control. So we would basically be almost manufacturing within our lab these plates. And so, but because of that, when we needed to scale, we were like, oh, why are we, this is one, obviously, like we had a forward and a reverse primer with different barcodes, but we decided that we also could try combinatorial indexing, right? We had 4 sets of we had 4 plates, each one had a 4 reverse primers, so maybe we can mix, the forward of plate A and the reverse of plate D, for example, to get a new plate, right? And so each of these barcodes, instead of being unique on both the ends, right? On one end, they would match 3 others, potentially up to 3 other samples. But we were able to verify that wasn't a big deal, but that allowed us to scale from 1536 to 6,144. So that's actually kind of, and that was able, with that, we basically were able to do 2 like sequencing runs of like 6,000 plus like a couple of the other ones. And so that was able to actually get us to 15,000. So then, so after we were doing that, we actually got this big grant from the NIH to buy all this automation equipment. And then we bought all this automation equipment, which we actually ended up, this is what the test looks like when it's fully automated. And that really allowed us to scale to 25,000 a day, which we thought that we would never really need, because this is like fall of 2021. But then like Omicron happened, and right? So then we were like testing a lot. Okay, so anyways, so that's so I think so in that sense, I feel like in terms of logistics, that problem is kind of under control. So anyways, but that's only for one test. But really, what about for more than one pathogen? So I feel like our next step, we were able to go from, so this is what we're able to do. So this is what we want to do. This is what we're able to do, right? So we basically developed a new test, and so I'm going to talk about that next, which is moving from one pathogen to kind of real metagenomics approach, so we can do a little bit more. So what's the idea behind that? So in some ways, I feel like our original goal was to develop the scalable COVID test. We did that, but really, we're in that whole project, we're using sequencing not for like sequencing. We're just using the sequencer itself as just a better PCR machine, right? As a PCR machine that could read more than an optical, machine, right? But really, the opportunity is really for sequencing. So, this is we got funded by BARDA and Amazon to develop a technology that can detect anything, and this is really just doing metagenomics. And so, I think that also while we're in this project, the technology landscape really changed because there are these new Illumina sequencers came out that are completely transformative, meaning that the amount of throughput that they have is just for cost is crazy. And that previously, when people were approaching metagenomics, they were very concerned about how the sequencing cost was the bottleneck. But I think that's really not the bottleneck anymore. And so now there's other problems. I'll kind of talk about it. So if you kind of look, if you think about what's the issue with this problem, so you have kind of the issue is that when you have a pathogen in a sample, the vast majority of it is human, human RNA, for example. It's like 99.5 is human RNA, and 0.5, actually 0.4 is like bacteria, and maybe 0.1 or less is the virus, right? So PCR actually is a great approach for this because you have this thing that's very rare, you have technology to amplify it, and then you can see it. So PCR actually makes a lot of sense. Other approaches are like depletion, so you can try to knock out all the human RNA and then sequence the rest. But there's another approach which is just sequence a lot, just sequence everything, right? So in the end, we actually do this third approach, and it's mostly because the quality of the RNA is so poor that when we're actually doing the sample and analyzing the samples, and you try to then measure to see if there's any RNA in the library, we can't detect it. But then when we sequence it, we see that there's something there. So the kind of regime of like low quality, is kind of off the charts. Like it's below the specifications of any of like the kits, but it kind of works. So there's very poor RNA. When we first started sequencing, like this is a kind of a histogram of the bases. So you can see it's basically sequencing the same sequence. This is like an adapter dimer. So the adapter itself, like there's so little RNA in there that the adapter connected to itself, and we just sequence kind of tandem repeats of the adapters. That's essentially what we're seeing. But after a lot of work, I think, I'm kind of skipping over, but basically over like 1,200 samples worth of optimization, we kind of went from something that was really poor to something that works. And I'll kind of give some results. So we got some data from UCLA Health, which they have a PCR approach that could detect 20 pathogens. So they gave us a bunch of positives of different viruses. And we end up getting about 460 samples, and then we basically ran it, and then we actually did pretty well. But the interesting thing is that we saw viruses that aren't, that they don't know, like are not on their panel, so they could never have detected. So for example, we saw somebody with influenza C, right? I actually didn't even know that there was an influenza C until I saw this. And then I looked it up in Wikipedia and verified that there is such thing as influenza C. But the entry tells me that it's not infectious in humans, right? So, so that's the thing. We also saw HSV also, so we saw other viruses there too. And we'll kind of get to that in a little bit. But what are kind of their new problems? So one problem is this issue of contamination. I think this is a really fundamental issue in this field. So here are like parainfluenza 3 is one of the viruses that we got positives for. So these are there are 5 positives that we know are positive based on this other technology. So we know they're positive. And then this is just this table showing the read counts for that virus in those 5 positives, okay? So you can see that the maximum read count is 1.8 million, okay? And the minimum read count is 16. But they're all known positives, right? So this is a range of like, 100,000, right? So that's one issue. You obviously will have a big dynamic range, but there's another issue, which is that if you have a tiny amount of contamination, meaning is that, let's say you accidentally in your process, there's many steps in your process, you put 1/10,000th of one sample into the neighboring sample, right? That'll create, like if you put 1/10,000 of E1 into your neighboring ones, that'll create a stronger signal than your actual H1. So this is a huge problem. And this is actually showing, this is actually where those positives are. And then this is like, when we first started working on it, this is where we also saw positives, right? So you basically see, this is a real problem. But somehow when we put it on automation, the automation is so slow. It's actually slower than a person could be. Like, in fact, watching it is really painful. So I think it actually doesn't have any contamination, because I think it's so slow that literally it waits for like all the little tiny droplets to fall. So that's actually, I mean, in some ways lucky that turned out. And we tried this for other viruses, and it's very consistent. So Okay, and also we did for saliva, but this is what the RNA-seq automation looks like. So it's I think it's like 12 hours of basically of stuff like this. So okay, I'm gonna kind of skip ahead, but yeah, okay. But I also want to say like what's like just to say like what is the future, right? So these are all of the Illumina sequencer flow cells that are under like 12 hours, like around around 12 hours or less, okay? And their cost, how many samples they can do, we can assume that we need about 4 million reads per sample. So how many samples they can do and what their cost is, right? So the smallest is the mini-seq, and that one actually can work in about 3.3 hours. And it can do 5 samples, but it'll cost about $220 per sample, right? But the biggest, but then on the, the stars are ones that we actually are able to do. So we're able to do about 100 samples with these ones and about 200 samples with this one. So we're actually able to kind of get to this part of the graph, right? But then if you look at, if you use the bigger NovaSeq X Plus, these bigger flow cells, you can get, the cost would be like $2, right? So this is kind of remarkable. And like today's instruments, you have 2 orders of magnitude difference in cost per sample. So this really says that, the way, in order to really make this work, you're gonna have to do a lot of samples at the same time, right? That's the only way to make it affordable. Okay, so anyways, the last thing I wanna say is bioinformatics. Okay, so how do we go to more pathogens than that? So, and I wanna, a few minutes on, kind of why is metagenomics hard? And really, I think, and the real thing is that genomic sequences from vastly different organisms can be similar for many reasons, both evolutionary and also introgression as well from pathogens. And there's incomplete reference databases. So what do I mean by that? So for example, let's say you have your reads and you basically align all your reads to SARS-CoV-2. For example, that's one scenario. In another scenario, you take all your reads from, you align it to either SARS-CoV-2 or human. And so in one scenario, in your first scenario, you'll have 3,000 reads mapped to SARS-CoV-2. In your second scenario, you only have 2,000 reads mapped to SARS-CoV-2. So there's basically 1,000 reads that look like they're SARS-CoV-2 in the absence of human, but when you see the human genome, you realize that they're actually human, right? So this is like, I think there's this whole Steven Salzberg, Rob Knight, cancer microbiome thing, right? I think those papers were finally retracted, right? But this is basically the reason why they had that problem. So that's one problem. So this actually suggests that what you should do is you should have as many sequences in your database as possible because then you'll be more accurate. But then when you have many sequences in your database, you have this other problem, which is that you have these called reference contamination. So you might have an unfinished bacteria genome, but it has a little bit of influenza or human contigs in there that you don't realize are not part of the bacteria, but they're annotated that way. And when you have human reads, they might map to that part of the genome, and your annotation will say that you have that bacteria present in your sample, which is, it's not there, right? So this is called reference contamination. So it's also the opposite. So if you add too many references into your database, then you're going to end up with incomplete references, and you're going to have lots of problems. So this is actually this is from Kraken. This is the kind of one of the common tools used. This is kind of what you typically see in a sample. You see many reads that are human, and then you have huge numbers of bacteria. And then when you look at the viruses, this is clearly a SARS-CoV-2 sample, but you also see some reads mapped to other coronaviruses, and some reads mapped to this like tomato brown rugose fruit virus, right? And it's 58 reads. So that's actually would be enough to call a positive in a different sample, right? So the question is, it's really messy when you get into this. And if you, so how do you, how can you tell if something's really real, right? So this is a fundamental problem. And I think that actually this is, if you want to work on something, this is a good one to work on. So if I want to go back to our results. So did we really see influenza C? Okay. So in our case, we were really curious about this, and we decided to just sequence the samples a lot deeper. So we put the same samples on a much larger sequencer and longer reads, and we ended up getting about 40 million reads per sample, which is about 10 times more than before. We assembled our sequence, and then we got contigs, and so some of the contigs would correspond to the virus, and what are we looking for? So we ended up with 173,000 contigs. Only 6 contigs, actually 7 contigs, are related to influenza C in this case. And how do we know that? We just see that there's a few contigs that span almost the whole length of the influenza C reference, and they have a very high aligned nucleotide identity. And so that's kind of what we're looking for. So if we see that, we saw that in this case. And so, for example, here's all our contigs. Virtually all of them have a very high aligned nucleotide, and they also cover almost the whole fraction of the reference. And so that's really good evidence that probably these are influenza C, and so they have all of their the reference names. And so kind of this is a summary. And the other thing that we did is we were wondering, well, maybe it's like a different influenza sequence. It's not in the database. We actually downloaded all of the influenza genomes that are in the NCBI, which is about 1 million. We matched our contigs against all of them. We got like 1,200 matches, and all of the matches. And so this is what the data looks like. And so then actually this is kind of inspired by last year's talk, Ryan's talk from last year. This is the command that I applied. Do people know what this is doing?
Is it a prompt for GPT?
Yeah, so it's actually the shell version of GPT. And so it's basically piping the annotations into GPT, and this is what it told me. Yeah, so it is. Yeah, so it agrees. It agrees. But basically, but I actually think that. So I want to kind of end here. What this is saying is that moving from 30 pathogens, which is let's say what we have now, to all pathogens is for to be really accurate is a really hard problem, right? I think there's many challenges, but I think that this is the kind of thing that CGSI people could really do. And so, for example, one thing is like we're now using RefSeq to move to NCBI and T. That's a whole set of problems. There's poorly annotated viruses. There's many. There's a million. There's like I think 10 million COVID genomes. Obviously, how are you going to deal with that? And then Logan and Serratus, what Ryan's talked about, that's like a different level, right? There's maybe 1 million viruses there, right? But there's no annotation, right? They just started, right? So, but the sequence is there. So the challenges are scalability, maybe annotation. Maybe we can use LLMs to help us annotate, and then also like database errors. Okay, so I was gonna talk a little bit about some minimizers, but actually if anyone can ask me that, I can talk about that later. And so yeah, so kind of this is where we are. Logistics, IT, I think that one I think we've solved. The assay, I think we're in the right direction. We can now do about 200 a day. It's not clear how we'll get to, let's say, 5,000 a day. And really, I think if it gets to that level, the price will go down to the right price. But it's in the right direction. And maybe we can do like 30. We can do kind of known pathogen, do some work to make sure it works. But how to move to kind of any pathogen, I think that's really hard. And then the regulatory, that's a whole. We're only started. Okay. So yeah. So this is the lab, and this is a lot of the faculty that have been involved. Okay. Thank you.